Hi everybody, this is Greg Bragg from Celestron. Today I'm going to answer another one of our dear Celestron questions. Today's questions is how do I choose, or which eyepiece do I choose, and what am I going to be able to see with the differences in from eyepiece to eyepiece? It's a great question, and it requires a little bit more than just answering a question, this eyepiece does this versus this eyepiece does this. It's important to understand a couple of things that control what the eyepiece does, and then we'll go through some of those things. We'll also talk a little bit about field of view, we'll talk about eye relief, we'll talk about the differences in eyepieces and how you actually calculate magnification. We'll also talk about some things that you can add between the telescope and the eyepiece to increase the magnification, and we'll talk about filters that enhance your observing opportunities. And then we'll also talk about a little bit about viewing in general and the night sky in general to help you understand more about how the combination of eyepieces and telescopes work to get you to the best experience possible, okay? I think we should start by talking more about the telescope and the eyepiece combination than the eyepiece itself generally, because there are some important things there for you to know and understand that will help you make the best decision if you're going to add eyepieces to your assortment. So behind me is a StarSense Explorer DX102. In that package of the Explorer StarSense Explorer telescopes, we give you two eyepieces. We give you a 25 millimeter and we give you a 10 millimeter, and somewhere there it is. I've got both eyepieces that are included. Now these eyepieces are basic eyepieces. Most all the other manufacturers that include eyepieces in their basic kits include something around these types of eyepieces. Now the eyepieces, the number on the eyepieces is the focal length of the eyepiece, and that's important for you to understand in just general terms, because a lot of people get confused by this number and they think sometimes that if you put a 10 on, it's going to be less powerful than a 25. Sometimes you put a 30 on, it's going to be more powerful than a 10. They don't understand the focal length relationship to the eyepiece and the telescope. So I'm going to give you some details about how that works and give you an understanding of how that will help you decide which eyepiece you need based on the object you're looking at. So let's start with this one. The 25, again, is the focal length, and the focal length is from the point of the entry of light, which is through the bottom, to where the eye is resting on the eyepiece. So that focal length is from this point to the inner objective, and that's how it's measured. There's a lot more to it than that. There's elements in here. Sometimes there's plastic elements. Sometimes there's really low quality. That affects your viewing as well. We include all glass in all the eyepieces that we offer. They are glass designs, but there's a differentiation in the number of elements here, which also creates some visual impact like contrast and sharpness and stuff like that. These are our basic series. These are great eyepieces for the beginner, but as you get more and more accustomed to using your telescope, you'll want to branch out and buy some other higher quality eyepieces to improve your visual, the visual experience. Now let's talk about how this eyepiece interacts with this telescope. I mentioned this is called the focal length. A telescope also has the focal length. This is a 102 millimeter, which is the outer objective diameter, the actual lens diameter across, which is equal to 4 inches. So this is a 4-inch telescope, 102 millimeter aperture, okay? This has a focal length just like the eyepiece has a focal length. There's a lens element in here, a diagonal here, and then the eyepiece fits into this area. When the light comes through the telescope, it's measured from the front element to the exit pupil of the eyepiece, which is where your eye sits. That's the focal length of this telescope. This telescope has 660 millimeters of focal length. That's important to help you calculate magnification. So in order to figure out how much magnification this eyepiece and this telescope in conjunction creates, you take the focal length of the telescope and you divide it by the focal length of the eyepiece. So in this case, 660 millimeter focal length, and a 25 millimeter focal length eyepiece would create about 26.4 times magnification eyesight. So what that means simply is that this eyepiece and telescope combination magnifies the object that you're looking at 26.4 times greater than you see it with your eye, okay? That doesn't sound like a lot of power, but to be perfectly honest with you, this telescope viewing Andromeda, which is 2.1 million light years away, which is a very big object in the night sky. You can't see it except in extremely good dark skies, but it's the size of 4 moons across. It's 2 degrees across, which is equivalent to 4 full moons stacked side by side, and with 26.4 times magnification, you can see Andromeda very easily with this telescope. Okay, now you also get the 10 millimeter, and if you change the 26 millimeter out to a 10 millimeter, then the 10 millimeter now, 660 focal length of telescope divided by 10 millimeters of focal length would now give you 66 power, okay? Those two eyepieces create that magnification combination. The 25 millimeter creates 26.4 times magnification, and the 10 millimeter eyepiece creates 66 times magnification. If you change to other eyepieces, you simply take the focal length of 660 and you divide it by the focal length of the eyepiece. That's how the math works, and that's how you figure out focal length of eyepiece and focal length of telescope to give you those combinations together to give you a magnifying capability. Okay. Next to the Star Sense is the NexStar 8 Evolution, and this telescope is a 2,000 millimeter focal length, which is equivalent to 8 inches in diameter in the front. So its front element is 8 inches, its focal length is 2,000. Wonder how this one, being short and compact, is more focal length than this one. This one actually folds the light into thirds. So the light comes through the front corrector plate, reflects off a mirror back here, goes to a mirror up in the front of the telescope, which is attached to the corrector plate, and brings it back to the diagonal and up to the eyepiece here. So it's basically folding the light. It's called a compound telescope, and that creates 2,000 millimeters of focal length. So let's go through our same equation very quickly. You put a 25 millimeter in the diagonal, and this telescope then would create 80 power with the 25 millimeter eyepiece, okay? 80 power with the 25 millimeter eyepiece. If you take the 10 and you put it on this telescope, it would create 200 times magnification. 2,000 divided by 10 is 200. So there's how you get the magnification on different types of telescopes. The focal length is the most important thing to know of the telescope and of the eyepiece, and then you just divide the focal length of the telescope into the focal length of the eyepiece, and that gives you the power. Can't be much simpler than that, really. But you do have to know the focal length of the telescope and the focal length of the eyepiece to get that. All right, beyond magnification, and magnification is not the ultimate answer to every visual observing situation. It is important to understand what the object is that you're looking at and what telescope and eyepiece combination works the best to look at that object. That's going to take some time and some experience getting familiar with your telescope and the eyepiece and telescope combination. Once you do that, then you'll have an understanding of what the 10 millimeter eyepiece does and what the 25 millimeter eyepiece does and how it affects how you see the object you're looking at. What we recommend for most beginners is to add 1 or 2 more eyepieces. You want one with less power, which would be 30 millimeter or 40 millimeter or 56 millimeter. That would be less power. And you want one with maybe medium power or even higher power. So that could mean you could end up with 4 or 5 eyepieces when it's all said and done. You don't have to spend a lot of money. We make a little series called the Omni, which are similar to the quality of these eyepieces. The barrels are metal instead of plastic, but all the optics are glass. And we have focal lengths from 4 millimeter all the way to 56 millimeter. So you have a wide range of other choices to add to these. You don't necessarily have to replace the 25 that you get and the 10 that you get. Add to it if you want to, and that's the least possible expense to get to other magnification capabilities. So I would recommend the 4, and I would probably recommend the 32, and that way, or maybe even the 40. That way you would end up with a 4 millimeter, a 10 millimeter, a 25 millimeter, and a 40 millimeter, and that would give you a nice range of magnification capabilities with this telescope. This telescope, because it has so much more power, I would recommend the same combination, but maybe in a little bit better quality eyepieces. This is a very nice precision instrument. The quality of the optics in this are much better than the quality in the StarSense, although both will give you great views. Don't be afraid of that. But because of the complexity of this telescope and the capabilities of this telescope, you're going to be able to see more objects and get a better advantage in that way with more eyepiece assortments. Okay, that's the basics of how magnification and then what options you have. Beyond that, there are lots of eyepieces on the market from lots of different manufacturers. There's probably 15 or 20 manufacturers out there of eyepieces, and they range from very inexpensive, $30 or $40 an eyepiece, all the way to over $1,000. The more you spend on the eyepiece, the higher quality it is. The more elements that are in there, the higher the contrast available in that eyepiece, the higher the resolution, the coatings are better. There's just a lot of advantages to adding higher quality eyepieces to your assortment. As you get more comfortable with the operation of the telescope and things that you enjoy looking at, then you'll want to research those other types of eyepieces. Okay, the next thing that happens in eyepieces is what's called apparent field of view. Apparent field of view changes the angle, the true field of view in the object that you're looking at through the telescope. The apparent field of view is, I guess the simplest way to say it is, let's imagine we're standing in a 360-degree circle, goes all the way around us. This eyepiece has a 50-degree field of view. So if we're standing in a 360-degree circle, we can see 50 degrees of that 360-degree circle. There are eyepieces out there that start around 40 degrees and go all the way to 120 degrees field of view. That's the apparent field of view, not the true field of view. And you can figure out true field of view. We're not probably going to go into that at this on this video, but apparent field of view and true field of view are two different things. Apparent is what you think you're seeing. What you actually see through the telescope is called true field of view. But the apparent field of view helps you see the object in a different way. An example of that would be like we defined Andromeda. It's 2.1 million light years away. It's 2 degrees across in the eyepiece. If you look at Andromeda with the 10 millimeter eyepiece at 66 power on this telescope, you're not going to see all of Andromeda. You're actually only going to see a small portion of it. But if you take a 10 millimeter eyepiece that has more field of view, 65, 70, 82, 100 degrees, 92 degrees, 120 degrees, all those field of views are available to you out there, then that will allow you to see the Andromeda galaxy at the same size, but more of it, because you're actually adding more field of view. That's the simplest way to explain it. The moon is a great example. The moon is relatively close. And if you're looking at the moon with the 10-degree eyepiece, you're not seeing the whole moon. You're not seeing any of the dark sky around it. You're seeing a small section of the moon. If you take the 10-degree that comes with the telescope, you're only going to see a small portion of that moon. It's going to be magnified greatly, but you're going to see a small portion of it. If you take a 10 millimeter with a larger apparent field of view, then you're going to see the same magnification, but more of the moon, okay? There is an advantage to that, and you should investigate that advantage, and you should look at other opportunities. We also make 56-degree field of view, 60-degree field of view, 65 and 70 degree, and out to 82-degree field of view eyepieces. They're more expensive, but they also offer much more contrast, higher quality glass, better coatings, and that increases the detail in the object that you're looking at, and is important for as you get more and more experienced at viewing. It's important to get a higher quality eyepiece to help see more detail. Those are the two big things that you want to understand about eyepieces. The lower priced ones offer a narrow field of view and aren't always going to be the highest quality and highest resolution. They're very acceptable for the beginner, and as you start looking through the telescope more and more, you'll see that there are reasons for you to add other eyepieces to your assortment, okay? We've talked about magnification, we've talked about field of view. Now let's talk a little bit about eye relief. One thing that the better quality eyepieces on the market offer is a larger, longer eye relief. I said three things: higher, longer, larger. You are able to get your eye farther away from the eyepiece. This eyepiece has a very small eye relief. It's 12 or 15 millimeters, is as far as your eye can be away to the front element. As you add a wider field of view, this is a 70-degree field of view, it increases the eye relief because it's allowed to have more glass in there. I'll talk about the size of this eyepiece in a second, and it'll be important for you to understand as well. But with eye relief, it's important to be able to get your eye centered over the entire exit pupil of the eye, of the eyepiece, and it's important that you're comfortable when you're doing viewing through these kinds of eyepieces. If you wear glasses, it comes with a rubber eye cup, and you just fold the rubber eye cup down, and this allows you to get it closer to your eye. But with the longer eye reliefs, you don't have to worry too much about that, and you can use glasses much better with longer eye relief. I don't use my glasses when I view. I actually take my glasses off, so that doesn't really affect me, but I like the eye cup up, and I like to lay my face right on the eye cup. All the eyepieces that we offer include a rubber eye cup, so it's comfortable to your eye. Okay, let's talk about the size. I didn't go too much more into the eye relief. Let me finish that. So comfort is the big thing with the more expensive eyepieces, and the eye relief it adds to that comfort, okay? Now, this is a 2-inch eyepiece. This is an 1.25-inch eyepiece. Most telescopes come equipped with an 1.25-inch eyepiece and an 1.25-inch diagonal. The diagonal is what reflects the light from the telescope into the eyepiece. The diagonal is almost as important as the eyepiece itself, because this is a mirror element in here, and there are better diagonals on the marketplace that increase the reflective capabilities of the light coming through the telescope and transmitting it to the eyepiece. So a diagonal quality is also important. This is a 2-inch diagonal. The 2-inch diagonal will then allow you to use 2-inch eyepieces. If you don't have all 2-inch eyepieces, they make a little adapter that allows you to put the 1.25-inch eyepieces in there. So that is able to use both 1.25-inch and 2-inch eyepieces. This telescope comes with an 1.25-inch diagonal, but can be fitted with a 2-inch diagonal. This adapter comes off, and a 2-inch diagonal similar to this one just slips right in, and now you can use 1.25-inch or 2-inch eyepieces on that 2-inch diagonal. The diagonals start around $75 to $85 and go up to several $100s. The 2-inch diagonal on this one would be give you the opportunity to use 2-inch eyepieces, okay? So that is an option available to you. Not every beginner telescope, intermediate telescope comes with the option for this, but that is something you should look into if you're interested in getting into 2-inch eyepieces and the higher quality eyepieces, okay? So this is a 2-inch, and it has the adapter to do 1.25-inch or put your 2-inch right in directly into the diagonal. All right, so we've talked about those things. We've talked about the basics behind choosing an eyepiece. We've talked about some of the options. We've talked about field of view. We've talked about 2-inch versus 1.25-inch. Now let's talk a little bit about what the sky does to your observing and how you have opportunities to improve that. If you're taking your telescope out in your front yard and your front porch light is on, your garage light is on, the street light is on right down the street from you, you're going to have difficulty getting your pupil dilated enough to see a lot of detail in the object that you're trying to look at. So what you want to do is try your best to get into dark skies. The darker the sky, the better. the darker the sky, that improves the opportunity then to allow your pupil to dilate more and to be able to see that object that you're looking at with more definition. That is a very important factor of being able to see a lot of the things in the night sky. If your pupil can't dilate large enough, your telescope can probably project it to the eyepiece, but because you don't have the ability to capture enough light with your eyes, you're not going to see the object that it may have found for you. The go-to telescope or the StarSense that uses the smartphone to get you to objects will get you there, but you may not be able to see them because of the inability for your pupil to dilate enough. And that's one big factor in visual astronomy. The darker the sky, the larger your pupil, and the better you will see the detail. All right, so that takes care of that aspect of visual. Again, you're going to use the same formulas to pick the eyepiece you want, to determine what object in the sky you want to look at. And the thing I always try to do is start with a medium power or a normal eyepiece, find the object, make sure it's centered in the eyepiece, and then change eyepieces through the observing experience on that one object and see what you like, especially if you're looking at planets. When you look at planets with a 4-inch telescope versus an 8-inch telescope, there's a pretty big difference. So you actually get a lot of opportunity now to see greater detail and stuff like that when you get to a larger telescope, and you'll want to have a variety of different eyepieces to take advantage of that aperture and to be able to see the details that you really want and that you paid for, right? Okay. The other things I want to talk about are things that you use between the telescope and the eyepiece. And you ask what that is. Well, there's a Barlow opportunity. There's a couple of different Barlows on the market. There's a 2 times, a 3 times, and a 5 times available. There's an 1.25 inch. There's also a 2-inch Barlow available. Those are additional magnification enhancements to the eyepiece. So this is a 3x Barlow. Now let's say we're going to use the 25 millimeter on top of the Barlow and then put the Barlow in the diagonal. And now what we've done is made this 25 millimeter a, what is that, 8.3 millimeter focal length eyepiece. So 8.3 now instead of a 25. And by using the Barlow between the eyepiece and the diagonal, now makes this 25 millimeter an 8.3 magnification, an 8.3 focal length eyepiece. So at 8.3 on a 2,000 millimeter focal length, you get about, I don't know, 300 or 400. I'll do the math real quick. 2,000 millimeter divided by 8.3, that's a 240 power on this telescope. On this one it's going to be much less, but you're still going to have the ability to see the object a lot closer. That is a nice accessory because you don't have to buy a 25 millimeter and an 8.3 millimeter eyepiece, although there is not one. There's an 8.5 and 8.8 and stuff like that. But you get an additional eyepiece. The other thing is you can take your 10 and put it on there, and now you have a 3.3 magnification eyepiece. And with this focal length, that's like 200 times, and you're close to reaching the maximum capability of this telescope. That's another thing I should tell you about. This is a 4-inch telescope. The rule of thumb is each inch of aperture gives you about 50 power. So this is only capable of getting you to about 200 power. This is an 8-inch telescope. It's capable of about 400 power. So you do have a lot more flexibility with greater magnification capabilities with this telescope because its aperture is larger. So because you have that larger aperture, you have the ability to use higher magnification, and using your Barlow on this would really be a lot more flexible. You would be able to use more eyepieces on this than you would be otherwise because of the magnification capability. Now, once again, if you get the 2-inch, you're going to need a 2-inch diagonal to use on this telescope, but it offers higher quality glass. It offers some more contrast and gives you a little bit better opportunity to still control your field of view. Now this also has the adapter for 2" or 1¼ and that's pretty standard on most every 2" diagonal and 2" Barlow, okay? All right, the last thing I want to talk about is filters, and then just a few things about observing in general. So filters are really a nice accessory because they add to the contrast and enhances the object that you're looking at. This is called an oxygen 3 filter. It's available in a 2" or an 1¼ and all it does is screw to the end of the barrel of the 2" eyepiece. And then what this oxygen 3 filter does is allows you to increase the detail and enhancement in a nebula object like Orion or the Pleiades or the Veil Nebula. There's lots of nebulas that are beautiful and they're very, very hard to see because they're not illuminated like galaxies and star clusters and stuff are. So the O3 enhances the vision, your visual experience when you're looking with the O3 on an eyepiece. There are also other filters for light pollution and creating enhancements with colors. Like if you look at Mars, they tell you to use a red filter because the red filter filters out the red, and you're able to see the polar cap and the mountain ranges on the planet Mars a lot easier. There's lots of filters out there from a lot of manufacturers, virtually the same kind of opportunity as the eyepiece manufacturers and the filter manufacturers. There's lots of options, but you should look into that. Last but not least, I want to talk about observing in general. One of the things that you want to make sure you're doing is relaxing when you view. If you're standing in a squatting position with your back arched and your head back, or you're reaching high on your tippy toes to look through the eyepiece, all those things create muscle tension in your body, and what that actually does is changes the shape of your eye. So when you change the shape of your eye, you aren't able to see the object as clear as you would if you're relaxed. So what I recommend is that you get an observing chair, or you take a small ladder out so you don't have to stand on your tippy toes. And when the telescope is low and you have to get to the eyepiece, you don't have to stand on your tippy toes. And the other thing, if your telescope is high and your eyepiece is low, then you want to be able to rest comfortably, sit comfortably in a chair, observing chairs that has adjustable seats, so that you're sitting comfortably and relaxed. If you're not relaxed, your eye changes shape, the cones and rods in your eyes are actually causing distortion, so you can't see the object as clear. So relax when you're getting ready to view. There's one more technique about viewing that works with your eyes, and it's called averted vision. When you're looking at a bright object in the eyepiece, let's say you're looking at Jupiter. Jupiter's a bright object in the eyepiece, and when you look directly at Jupiter, the amount of light that comes from that object is going to be overwhelming to the cones and rods in your eyes. So what you want to do is you want to look off the side of the object, kind of look to the left or right of it, and use the edge of your eyes by looking just to the edge of your eyes to be able to see that object with more detail, because the cones and rods on the outer edge of your eye are going to be as sensitive as the ones in the center, but they're not going to be overwhelmed because you're not looking directly at the eye. That's called averted vision. Averted vision is something you have to teach yourself and you have to learn. But if you're looking at a very faint galaxy in the eyepiece and you can't see it, if you look away from the center of the eyepiece and let the edge of your eyes look at that, you'll actually see more detail than you would if you just look straight at it. So those are some tips and tricks on how you can improve your visual observing. I hope this didn't overwhelm you. There's an awful lot that goes into the combination of eyepiece and telescope, but hopefully this has given you enough information about what to use, when to use it, how it works, how the magnification capabilities change what you're looking at, and how you calculate all that so you can take advantage of the scope and eyepiece combination. That will be a good start at getting out there and getting some great visual observing done. I really appreciate you listening. I look forward to talking to you again sometime soon. Thank you very much. Goodbye.